In the last video, we have discussed about the edge-triggered SR flip-flop and edge-triggered JK flip-flop. So in this video, we'll be discussing about edge-triggered JK flip-flop. So how are we going to build this JK flip-flop? So this was the SR latch, this S bar and R bar. Upon that, I was making that into a JK. So this was an S input and R input that have rewritten as J and K input. One additional thing, if I want to make this SR into JK, is this feedback. This Q bar has to be connected with the J input NAND gate. This Q has to be connected for the NAND gate where we have given K as an input. So this is an additional to convert SR into JK. Now I want to make this as a flip-flop. That's the reason I just make this as a clock input. So whenever I just make the gated to a clock, there will not be much changes. The gated, we just write it as a gate latch. Here I'll call that as a flip-flop. So whenever this was 0, the clock input is 0, irrespective of the J and K input, it retains with the previous state. When the clock input is 1, based on the J and K input, we'll be getting our output as different values. No, the clock is 1, J and K is 0, 0, then it is previous state. Clock is 1, J is 0, K is 1, it is reset. So it is Q is 0, Q bar is 1. When clock is 1, J is 1, K is 0, it is set. So Q will be 1, Q bar will be 0. If clock is 1, J and K is 1, 1, it is toggle. If my Q was there before 0, now I'll be getting 1. If it was 1 before, then I'll be getting 0. Q bar is reverse to that. This is for the truth table of the JK flip-flop. Now we'll just check with this working condition of the JK flip-flop with the circuit. So now I'll just assume the previous condition with some value. Okay, J is 0. Sorry, Q was 0 before. Q bar is 1 before. So 0 and 1. And here the conditions been written with the J and K for 1. So with the toggle case, let me work with this toggle case. Later we move on for the other cases. Okay, Q is 0 here. So if you just take J and K is 1, 1, we can't decide the output of the NAND gate. If any one of the input is 0, then we can decide it easily. The output of the NAND gate is 1. Okay, that's the reason I'll consider this previous state. So here it was 0, 0 here. So this is 0, K is 1, and the clock has been applied. So one of the input is 0 here, the output is 1. So I'll be getting this 1. So this was 1 here. So 1, 1 and 1. All these are 1, output is 0. So I get 0 here, I get 1 here. 0 and 1 with the S bar and R bar. When S bar is 0, it is set. So I'll be getting Q as 1, Q bar as 0. So I get this condition 1, 0. Now I'll be working with the next contents. So if this is my present state 1, 0, I'll be providing this as a feedback now. So now the 0 is the input applied across this. J and K is still 1, 1 only. Whenever this is 0, one of the input for the NAND gate is 0, the output here is 1. So this S bar will become 1. Here it was 1. So 1, 1 and 1. The output here is 0. So 1, 0. Now S bar is 1, 0. Then it is reset. So we get 0 and 1. So this is how the toggle condition of the JK flip-flop will work. Now we can just look in with the reset, the reset and reset conditions here. So what I can do is I'll consider my J input is 0. Okay, so consider the J input is 0. Yeah, anyhow it is reset condition. Let me not make it with 0. So I'll consider my J input is 1, K input is 0. J is 0, the output of the first NAND gate is 1. So as soon as this is 1, what is the output here? Because k is 1 now, this 1 has been fitted here, 1, 1, 1, the output here is 0. So the output of the first stage of the NAND gate is 1, 0 now. When S bar is 1 and R bar is 0, it is reset. So we get 0 and 1. So with J0 and K1, it works as a reset condition. If both are 0, 0, J0 and K0, how it will work? Now we'll consider the present state is 0, 1 is the output, okay? When both are 0, 0, output across this is 1, 1. So output across this is 1, this is 1. When S bar and R bar are 1, 1, output is previous state. So the previous state output was 0 and 1 here. So we get the same state 0 and 1. This is how the JK flip-flop will work. So now we discussed all the cases with respect to the clock when we apply, right? Now very important thing is when there is no clock, what will happen? When there is no clock means clock is 0. When clock is 0, one of the input of the NAND gate is 0, then output is always 1, 1. When it is 1, 1, it stays with the previous state. Irrespective of the input, output is the previous state. That's what has been written here. Now, as soon as I apply the clock and I provide the J and K input, I'll be getting the output here. In case of the toggle condition, when J and K both are 1, 1 and the clock is 1, for every apply of the clock, my output work like either set, reset based on the input. So now, when J and K is 1, 1 and with the application of the clock, what happens? Within the single clock pulse, the output toggles multiple times because J and K is 1, 1 and the clock is 1 now. As soon as I get here 0, the 0 has been fed back here. I'll be getting the next state as 1. So 0, 1, 0 like that. I'll be having multiple times the output varies within the single clock. A single clock. That condition is called a race around condition. This is the drawback of the JK flip-flop. In order to overcome this drawback, we can go with the master-slave JK flip-flop. Next, we'll be discussing with the master-slave JK flip-flop.